This is a short instructional video describing Wilson, Tang, Zarin, and Selina's Final Sixes project, in which we built a MATLAB application that can be used to demonstrate and visualize important control system concepts. So our MATLAB GUI essentially has 4 diagrams. It will show you the Bodhi plot of whatever control system, and you do this by implementing and entering in a transfer function in this form right here. It will also demonstrate the pole zero map and calculate and plot those for you. At the same time, I'll also plot the step response. As you can see, each of these variables, so A, B, alpha, and W naught, are all variables you can enter. So for example, if I enter 0, 1, 0.665, and 1, and I click no feedback, this is what you get. At the same time, you're able to use the sliders to adjust the value, right? So increase by some amount, or just type it in yourself, and then it will readjust the plot after a short delay. As you can see, the plots are changing, right? If we adjust alpha a little bit, as you can see, the step responses change, the Bodhi plot will change slightly. At the same time, we also have implemented three common feedback controls, which are proportional control, integral control, and differential control. Now you control these the exact same way that you control the sort of general transfer function. You can either type it in, and you can increase with these sliders. At the same time, the final one, PID control, essentially will take a combination of all 3 of these. So if you enter, and at the same time, if you only enter values for 2, it will basically only do, for example, proportional control and integral control. So sort of to showcase that this is accurate and to demonstrate the effects, if we were to enter in a general transfer function with this form, so if this is the sort of no error, no controls feedback step response, this is what it looks like. And as we can see, we're trying to approach some set point, but we're not doing it so well. So when we implement proportional control, starting with, let's say, 1, we can sort of improve the rise time, right? It's approaching the set point much faster. And as we increase the sliders of this value, we're improving how fast it rises and how fast it approaches our set point. Now, if we now add an integral control, right? So starting at some value of 1, at the same time, it will reach it, but it also removes the residual steady state error. And if we were to sort of increase this, it sort of gets better and better. But at the same time, we have all these oscillations, so we can now implement just differential control, which usually undamps systems. So if we put this all together, right? So if we just put Kp and Ki as a proportional integral, we get something that looks like this. So it's able to reach it, but we see it still takes some time to settle. Now if we now add in the sort of Kd component, and click this again, it's settling much better. And if we increase it, then it improves. And basically, as we can see, once you sort of get to about 3 or 4 for this particular transfer function, we can see the effects of PID control and why it's so powerful, in that you can sort of tune whatever step response to make sure that you're only getting what your set point Y SP. So that's it for our video.